Okay, so today we're going to be talking about UML. I've hinted at this a little bit throughout the prior few lectures because we've been looking at some class diagrams and some relationships between these class diagrams in ways that we want to be able to read these diagrams so that we can understand very complex class interactions that we're going to be talking about when we start talking about design patterns. I anticipate this will probably only take us a couple days, despite the fact there are 56 slides in here. There's not that much to them. The most important thing is analyzing all of the visual diagrams that will be embedded in these slides to be able to talk about, all right, here's an example of this. What does this mean? But let's start by describing and looking at the concept of modeling. So what does it mean to model something? Well, it means we're going to be looking at that at a high level of abstraction. If you can think about writing code involves, in an object-oriented world, writing classes, and these classes are going to relate to each other to solve some kind of problem. So zooming out of just the individual classes and the lines of code that are written in the class, we want some language, some visual language of being able to describe how our application works, what it's doing, what are the associated things and relationships within this application that anyone can understand. It doesn't have to be a programmer to be able to understand something like this. And it allows us to be able to communicate with our clients. It allows us to be able to communicate within departments of our company. The coders can talk to the non-coders, can talk to the support staff, can talk to those who are just there to do quality assurance. There's a common language that allows us to talk about what the code does. Over time, UML has kind of changed, or I guess it's not necessarily UML, but the modeling languages have changed from state machines. And the concept of state machines just say that you have some internal state representation. Here's where the program is right now. There are transitions between those states that are defined by actions that someone can take while operating the system. When I'm on this screen and I click this button, then I end up on this screen. So you'd have two states representing the two screens, and the transition would be the clicking on the button that transitions you from screen A to screen B. Something like that. So that's the concept of a state machine. You want to know all the different kinds of state machines, you should take compilers from me eventually. We've talked about lots of them and the power of them, what they can represent, what they can do. Entity relationship diagrams. So what are the actual objects that can be instantiated in this code, and how are those objects related to each other? And also data flow diagrams. So where is the data being housed? How is that data being passed around or shared? And what associated data does each particular object have access to? How is data generated? How is data stored? And who has access to what particular kinds of data? So all of these kinds of notations have kind of merged together into, there are lots of different kinds of UML diagrams, and we're going to talk about quite a few of them, and I'll point out the really important ones for this course. But I at least want to introduce you to some other kinds of UML diagrams so that if you see them around the internet in future classes as ways of describing things, you at least know in general what they are. I included a very brief amount of history in this because usually the history is not incredibly important to the modern day use of it, but there are a couple things that are at least worth pointing out. If you're going to come up with some pros and cons of UML, part of that just stems from how UML came to be. So in the 1980s, we had a big shift toward object-oriented programming from procedural programming. So we needed some way to model the object-oriented universe we were beginning to find ourselves in. By the early 90s, there were over 50 of them, 50 different ways to describe how objects interact and being able to visualize objects kind of from the top down. So that was the 80s, and you can imagine if there are 50 different kinds of modeling languages, you need to know 50 different kinds of modeling languages because you don't know which one you're going to end up seeing in a particular context. So in the 90s, we discovered that this was a large problem. And so three of the leading notations decided to all combine together to make a unified modeling language, which is what UML stands for. Why do we do this? Well, the modeling languages kind of naturally move and evolve towards each other because we want one way of describing it, but there are lots of different kinds of diagrams that can describe different things. So we wanted to be able to set some kind of industry standard that allows us to be able to describe any application, any object-oriented application at a high level. So UML stands for Unified Modeling Language. It was designed kind of by committee. There were lots of people who said, but my diagram does something that nothing else in this collaboration does. We should include my diagram or merge my diagram type somehow into this unified modeling language. And everyone wants what their particular favorite approach is to be what the industry standard is. Think of this like an argument between you and your friends about what your favorite programming language is. There are so many different opinions on this, and everyone wants their favorite programming language to be what has the most jobs available for it. So how do we all come to a consensus about what jobs should be done in what languages if everyone wants to program in a different language? So the resulting design of all of this work was this absolutely massive modeling language that included tons of different diagrams, bunch of different features. There were completely unrelated styles of this that were still considered to be underneath UML. So if you're familiar with set notation, this could be considered to be something like the union of all modeling languages. Basically just if there was a modeling language, UML was trying to incorporate it in some sense. So the history, even still, UML is a very strange concept because there are very few specific kinds of diagrams that can be done in exactly one way. And you'll find that even if they convey a relatively similar idea, two different ideas about how to communicate that may look a bit differently. So approaching a UML diagram, you'll want to think to yourself, what is this diagram trying to show me? And there are some things, though, that are consistent across all UML that we've come to have as an industry standard. So that's really what I want to portray in this lecture is what pieces of UML is there really only one way to describe so that when you see it, you can recognize it. So we're going to discuss a bunch of different kinds of diagrams, use case diagrams, class diagrams, object diagrams, sequence diagrams, activity diagrams, and state diagrams. And all of these different kinds of diagrams is still just a subset of UML, but I've selected the ones that are most likely to be used, you're most likely to be seeing around as you get more experience. So we'll just kind of go through these and try to figure out, okay, what are they? When are they used? What are they describing? How do you make one of these? So a use case diagram, we have actors who are the people using the system. And each of those people using the system are going to use the system for a different reason or a different purpose. We're going to call those use cases. What is this person trying to get out of this? One way to describe a use case like this is, as some user of this system, I want to do something that I want to do so that I accomplish something that I want to accomplish. So there's this kind of, I want to, so that language that you can always use to describe a particular use case of a system from a particular perspective. You want to know more about this? Take software engineering and especially take it from me, because we will be writing use cases as we design a large-scale application. And if you take it from me, that large-scale application is going to be an editor for UML class diagrams. So you're going to be making the ability for someone else to make one of these, which kind of is a double thing. Anyway, it's a really cool project that, while it's not super thrilling to produce, is very technical, very useful, and employers will eat it up. I teach it next fall and next spring. I am not necessarily completely advocating for that, but I'm advocating for it. You should take it from me. It's cool. It's hard, but you'll learn a lot. So here's an example use case diagram for something that we all probably have experienced at some point. So we have here some kind of restaurant. In the restaurant, there are lots of different people who engage with the restaurant in different capacities. So we have waiters, clients, cashiers, and chefs. Each of them interact with the restaurant differently and have different needs out of this restaurant. And interacting with it looks very differently. So the client, for instance, can place an order and can pay for what they have consumed. They can also eat what they have paid for. So there are just kind of relationships between this client who's using the system with the concept of maybe we have a class for ordering food. We have a class for what is it like to eat food. And by that, it's when someone is eating, what needs to be done? How would the cashier, or the waiter, or the chef, what would that look like if we're in the eat food, if that it's been instantiated and is currently ongoing? On the other hand, the waiter can receive an order. So everything that is kind of an arrow here with a name on it, that would be a method or something that this can do in order to make this object. But note how making these objects mean that other actors in the system now can interact with that as well. So the chef may need to confirm the order to make sure if there's any ambiguity in the order that that's actually what was intended, or that's what the client wants. Because if the chef makes something the client doesn't want, that looks really bad. On the other hand, there's a cashier. The cashier really only accepts payments. And you can see that there's an extension here for eating food and drinking wine, since the actions that you would take while drinking wine is basically the same as the actions you would take while eating food. So you can lump them together into one class hierarchy that allows you to make a superclass for that possibly. But this doesn't fully describe any of the application, how any of this code is written. It's just a very high level diagram describing how the system works. Do you need to be a programmer to understand this diagram? Not really, right? If I were a restaurant and I wanted a digital system for my restaurant, if I was looking at something like this diagram, I could determine, is this what I want, yes or no? You might have some questions about it, but you can come up with those questions based on this. You can have a discussion about the code at a higher level than just the code, which is extremely important in industry. Anyone have any questions about this diagram? Who the actors are, what they can do, how this describes a system? So this is a use case diagram. It's really only describing who are the actors and how do they interface with the system. Here's an example of another system. We have a project and resource management system, and we have some actors. We have a resource manager whose goal is to manage resources, a project manager whose task is to manage projects, a system administrator who does all of the administrative functions of the system, a backup system for housing backup data in case something goes wrong. So this is a use case diagram that does not describe anything about how resources are managed, or how projects are managed, or how the system is administered. Says nothing about any of that. And you can imagine that this little bubble right here, you could zoom in and have another use case diagram for how the resources are managed and who might be the actors in that subsystem. You could zoom in on this. So you can have different levels of UML diagrams representing different levels of abstraction of the system. And you kind of move between those diagrams as you wanted more or less levels of abstraction in the system. You would start by looking at this and say, okay, there are 3 main managers and administrators, and they do stuff. And then you could look at other UML diagrams to further define what that stuff is. But that level of abstraction is really useful for talking about a system, a complex system especially. So now if you wanted to zoom in on the project manager, they can add, remove, and update a project. If you remove or update a project, we need to figure out which project they are talking about. If they're adding a product, it's not part of the system yet. So we're gonna make it and then add it to the system. But if we want to remove it, we have to go find it so that we can remove it. If we want to update it, we have to go find it so that we can update it. So a project update can involve some subtasks, adding, removing, or updating an activity, adding, removing, or updating a task, or assigning some resource to a task or unassign a resource from a task. So all of those are ways that this system could work. Again, this is just an example of a system, but it's zoomed in from the last one. We're talking about the project manager managing projects. So that subsystem would look something like this. This is the zoomed in diagram from that particular perspective that says we have the project manager. The project manager can do one of 3 things, add, remove, or update. And as parts of those, here's how those interact. What needs to be done if we're going to update a project? Well, updating a project can be defined. This is why we have all of these extends, because this is now an inheritance hierarchy. Update the project is the superclass. And these subclasses are things like add a task, remove a task, update a task. All of these may involve something like a database connection or something that involves us needing to go get that associated thing. And you could potentially move that up to the superclass, which gives us reason to have this particular inheritance hierarchy. But it allows you to see that there is a hierarchy associated with this. And a coder could look at this and go, oh, this is an inheritance hierarchy. And if you're the client, you go, yeah, that seems about right. They don't get the fact that this is an inheritance hierarchy, but different people, when they're looking at this diagram, are going to get different things out of it. All right, so use case diagrams are really good for high-level understanding of projects and tasks. Class diagrams, on the other hand, are made for computer scientists. This is going to be the single most important one that we cover today, because this is mostly how large-scale applications are broken down to describe, all right, programmatically, what are the components of the system? So a class diagram is going to explain a class at a high level. Again, it's not going to tell you about the implementation, but it's kind of like an interface. It tells you what are the fields, what are the methods. For the methods, it'll tell you what the associated parameter is. For the fields, notice that there's no type here. You can include or not include the type of each of these variables. This question mark tells you that it's a Boolean. Whenever you're asking a question, the answer is either yes or no, true or false. But other than that, the level of detail that you put into this is kind of up to you. And the reason that is you might have different types called different things in different languages. We're going to go into relationships next, because if you have a class like this, classes are often related to each other in some capacity. So we need to be able to describe how classes communicate to each other, or what classes are subclasses of other classes, or what classes describe the behavior implemented in another class. So lots of different kinds of types here. We'll start with either directed or undirected association. We'll go into reflective association, multiplicity, aggregation, composition, generalization, and realization. There are other relationship types, but these again are far and away the most commonly used. All right, association. This is the most general kind of relationship between classes. This is where you go if there is no other more specific relationship between classes that you want to use. So I talk about it first, maybe I should talk about it last, but the idea is there's some very loose connection between these classes that cannot be further specified with specifics. So an example is an airplane passenger and an airline. This is not the airplane, this is the actual airline. So when you're sitting on a plane, that's a particular type of plane, where there are particular, that plane is in a bunch of different fleets of a bunch of different airlines, but you're flying a particular airline. You're flying Alaska or Delta or Southwest or American or United, and there aren't any others because it's a stupid oligopoly. Anyway. There's a relationship here, obviously. You're flying a particular airline, but does it affect the behavior of anything really? Is there any real connection between this other than just it's kind of abstract? You're flying an airline. It doesn't change much about the actual process, about anything. So if we're describing this, these are the class diagrams that were on the last slide. So these would often be broken down into having their own fields and methods. So these are class diagrams. The way that you're going to show an association is you're just going to draw a line between. Not a fancy line, nothing on either end of it, just they're related somehow. Note that this direction is also kind of bidirectional. There's no directionality to it, where a passenger is flying an airline and an airline has a passenger. So it's not as many passengers. So it doesn't really, on multiple flights. So it's not really directional. It's not like this causes that or this. It's just an association, a generic association. However, there are some that should be directed, that says that there's a kind of a flow, a cause and effect, or there's a direction to that association. So an example here is an airplane and its passengers. So not an airline anymore, but an airplane has passengers. A passenger is a passenger of a particular airplane, but you can kind of see that there is directionality. An airplane has passengers. So we want to draw an arrow in that case from the container to the containees. So the container in this case is the airplane. It contains passengers. So we want to draw an arrow from the airplane to this passenger class. Shows the directionality of the association. Questions on association or directed association, how you might come up with the fact that it's an association, whether or not it's directed? All right, reflexive association is very interesting. And this is when you can have one class that can have lots of different potential instantiations, can have multiple responsibilities. So you instantiate a class and further specify this is this particular kind of that class, or this is this other particular kind of that class. So as an example, we have this generic class, airline staff member, that could possibly be a pilot or an aviation engineer or a ticket dispatcher or a guard or a maintenance crew member. All subclasses of this pilot, of this staff member. You can think of the fact that there may be a manager-managee relationship within this same superclass. So the aviation engineer may oversee the maintenance crew member and be responsible for managing that particular staff member's responsibilities. We can include this concept of kind of counting the number of ways this could be instantiated. So if you see in a diagram a number ... star, it just means that many or more. So a diagram, what this might look like is you'll have kind of a self-referential arrow saying that, all right, there is an association between this class and itself. How many of them are there? We don't know. It could be a one-to-one relationship. It could be a one-to-many relationship. It could be a many-to-one relationship. And in this case, we have a many-to-many relationship. So we don't know how many are on the outgoing edge of the reflexivity and how many are on the incoming edge. It depends on who we're talking about and the multiplicity of that relationship. It just says that a particular instantiation of an airline staff may be associated with another airline staff in some capacity. This one may be the least useful one we're going to go over. We don't see this quite as frequently, but it still happens. So it's good to know if you see something like this, what it means. Questions about reflexive association? All right, multiplicity. This will communicate how many of something is related to how many of something else. So the set term for this is the cardinality of one class in relation to another. What we mean by that is something like an airplane and its passengers again. So there was a directed association between these, but there's also a multiplicity relationship that tells us things like, can a passenger be in multiple airplanes at the same time? Can an airplane be empty and have no passengers in it? Can an airplane have 2 passengers in it? Can an airplane have 50 passengers in it? So we need some way of describing this. So the first thing we can note is that an airplane does not need passengers in order to operate. A plane can be flying without passengers. Since this is an abstract airplane class, we're not particularly focused on a particular airplane. We could provide an upper bound if we knew exactly how many seats were on this airplane, but it's an abstract class, so it represents a generic airplane. We don't know if it's a small plane or a really large plane, so we're not going to bother with an upper bound to the number of passengers. It doesn't stop becoming an airplane after there are 200 passengers on it. It's still an airplane. So because of this, we're going to show, and there should really be an arrow here, but there is a relationship between airplane and passengers where each airplane has 0 or more passengers. So assume that there's an arrow for the directed relationship here, but you can add a number here that shows as we go from this to this, one of these contains 0 or more of these. How are we doing? Good so far? Makes sense? Now we come to the difficult one. All of these so far have been relatively straightforward, and we're going to come to 2 of them that are frequently confused. This may have been covered in 211. You will have to tell me, have we talked about aggregation versus composition? This will be an excellent conversation then. So these are 2 different kinds of relationships that are very closely related and frequently, very frequently confused because their definitions are very similar. So in aggregation, it's a particular kind of association where one class belongs to a collection and the other class does not. Any particular object can exist in multiple collections. And the most important thing for distinguishing this, no ownership is implied in this directionality. So the container does not own its containees. If you're going to make a relationship arrow between these 2 classes, you're going to have a hollow diamond on the contains side. Composition, on the other hand, we again, one class belongs to a collection, so this is the same between both an aggregation and a composition. But in a composition, there is no such sharing. There cannot be 2 different objects that have the same object in each of its collections. So there's a particular ownership or has a relationship between the collection and the collectee. So there's a filled diamond on the contained side of a composition. Is there anything I can make clearer definitionally before we get a couple of examples to be able to determine the difference between which one is aggregation and which one is composition? To me, the best part of this is ownership. All right, so here are two relationships missing the hollow or filled diamond part of the relationship. So a car has 4 wheels and a project has 1 or more consultants. Which one of these is aggregation? Which one of these is composition? Aggregation here, composition here. Any agreement or disagreement? Most people agree, a couple of people disagree. For people who disagree, what makes you disagree? Yeah.
Can a consultant belong to more than one project?
Maybe. Can a wheel belong to multiple cars? Does a project own its consultant? Does a consultant own the project? Does the car own its wheels?
I got the definitions backwards, my bad.
It's good. So, yeah, we have composition on the left and aggregation on the right. To me, intuitively, the reason a car owns its wheels is you cannot have a wheel, the same wheel, that is on multiple cars at the same time. However, a consultant may be on multiple projects, but that's not necessarily the directionality of this. The question is, can the same project belong to, sorry, can the same, yeah, I don't want to say that. In the scope of this containee relationship, this is the containee, this is the container, the consultant is working on the project. So we can't necessarily have the same consultants. The same consultant could kind of work on multiple projects, which is why that doesn't really work as well. I think ownership is the easiest way to see this. Does a consultant own the project? Not necessarily. Does the project own its consultant? No, the consultant can be on multiple projects. Does the car own its wheels? Yes, those wheels cannot be on multiple cars at the same time. Ownership is the easy answer to this. How about this example? We have our class and you all, and we have this building and its classrooms. Which one is aggregation and which one is composition? According to the prior thing, they should be 0 ... star, not just star. Just giving a notation update here.
Wouldn't aggregation be on the left?
Aggregation on the left, composition on the right. Agreement, disagreement? What makes you say that? To anyone, not necessarily just the person who answered. But what makes you think that aggregation is on the left, composition is on the right?
Student can be in multiple classes.
Yeah. If you think about this particular course, does this course own all of you? I mean, maybe, depends on the difficulty of the exams, but I don't say that just to be confusing. So here we have an aggregation on the left, yes. Does this building own its classrooms? Yes, this classroom cannot exist in multiple buildings at the same time, unless you're on the WSU campus, in which case there are some pretty confusing classrooms about which building they belong in. If you're in the, never mind. Not related to this. Like 5 buildings in one building over there, it's horribly confusing. But in general, yeah, the building is gonna own its classrooms, but a student may be in multiple classes. This isn't the only class that you have. So because of this, it is aggregation instead of composition. So again, I go back to that ownership. Do you really own the thing? Does this class own its students? No. You're free to get up and leave whenever you want. Can this classroom get up and walk out of the cat? No, it can't decide to do that. Let's also now look at a code example. So here are two different implementations of the car class. One of them there's composition on the left and there's aggregation on the right. Try to tie the definitions that we talked about to how that is embedded in the actual syntax, the actual code of this. How is it apparent which one is composition and which one is aggregation? Talk to your neighbor. I feel like this is a good social opportunity for all of us antisocial people. Talk to your neighbor, figure out why does this make sense? What are the differences between the two and why are those differences there? And what do they say about the associated objects?
Yeah. Yeah, apart from that. It's like.
If you think about it. You can also buy it.
But not
getting such a. Once you get the engine, you can.
But the engine doesn't. On the right, that's changing.
Do we feel like we have an intuitive idea of how these are different and why they're different and how that maps to the definitions of composition and aggregation? What do we see? Yeah,
So on the left, first thing I was understood that engine is file.
yes.
And then like in a constructor, it makes a new engine object every time it's constructed.
Yeah, so the engine is part of the car's construction. And the engine cannot change. Right? We can't make any modifications to this engine. Once the engine is put in the car, it's finalized. It is in that car, cannot be removed, cannot be changed. It's part of the car. That means the car owns it, right? There's no other, you can't take out that engine and put it in another car. What about on the right? Are we able to remove the engine and move it between cars? This final, there's lack of final here, says that it can change. And the fact that when we assign it in the constructor, here we're making the engine directly from the specifications. And here we're doing a shallow copy of an existing engine. So the engine is made separately from the car and then they are combined together. Which means that there is a separation between the concept of a car and the concept of an engine.
You have a bunch of cars on the same.
You could. You could do that. And note that now a car is not defined by an engine, so we have to check whether or not the car has an engine before we make the engine do anything. Whereas before, there's no way to have a car without an engine, so we don't need to make that check. The engine happens in the constructor, so we can't have a car without an engine. So there's no right or wrong way to produce a car here. These are two different kinds of design decisions you might run across. If you're making a car, you could make a car in one way or the other way. But the difference here is important because it defines how we're going to use the object, what it can and can't do, etc. Does anyone have any questions about this code and how this works together to create Hopefully this distinguishes composition and aggregation. This is at the 211, 212 level, one of the big roadblocks to understanding. It's one of the most frequently misunderstood concepts. So if you have any questions now, feel free to ask. If any questions develop as you study this material or try to go implement something that has to do with it, you can let me know at a later date, but I'd be happy to answer any questions you have now. All right, the next type we're going to talk about is one we're all pretty familiar with. Generalization, which is really just inheritance. So the way we're going to signify inheritance in a class diagram is we're going to have an open or a hollow triangle. This is the superclass button. Can we instantiate a button? Well, we don't know what it's for. Is it for requesting anything, or is it for denoting that some emergency is happening? What happens when you push the associated buttons, whether it's a request or an emergency, is going to be very different. If it's a request, maybe one person gets notified of the request. If it's an emergency, then a lot of people are going to be notified that something has happened. So the buttons do very different things. We can't instantiate a button without further defining what kind of button it is. So we will say, here's the superclass. Here are the subclasses. Here's another example where there is a multi-tiered hierarchy. We have a generic doctor class. A doctor can either be a hospital doctor or a general practitioner. And the hospital doctor, the only kind we have at the moment is a cardiologist. But you can imagine that there are many other kinds of hospital doctors that would inherit from this general superclass hospital doctor. So we can have an inheritance hierarchy that is defined by multiple levels of inheritance, multiple levels of superclasses. Questions about generalization, what it represents, or the associated symbols you should be using for this? Once again, I want to point out these are all class diagrams. So even though this just says the name of it, usually if this is a full diagram, you would have the actual fields and methods listed for each one of these rectangles about what each one of these classes actually contains as far as state and behavior. The last one we are going to cover is called realization. This is where we have some functionality defined in a class that passes that functionality onto the actual object that implements that functionality. So here we have two classes, a printer setup and a printer. In order for the printer to work, it needs to be set up first. So in order for the printer to work, we have to do everything defined in the printer setup class. That's what realization means. This isn't a usable object until this has been done. So denotes the implementation of functionality defined in another class. You have a broken line with an open triangle. So it looks very much like inheritance, but it is not inheritance. It's a broken line instead of a straight line. You want to have the from being the associated work that needs to be done first, and then the to direction is the item or the class that doesn't function without this functionality. Questions on realization? All right, we're kind of transitioning at this point into a different part of this to talk about the other different kinds of diagrams. I don't know if I quite want to get into those with just a few minutes remaining, so we can leave a few minutes early. We haven't really done that this quarter, but I think we have just about one full lecture left of the remaining half, which will put us right on schedule for what I want to be doing. Are there any general questions about UML diagrams, anything that I can answer? Otherwise, you're free to pack up and head out, but any questions I can answer? All right, I will see you all tomorrow.